Hello and welcome to the European Union site event on MOSAiC, the greatest Arctic expedition of our time. My name is Fritz Habekus. I'm a science editor at Die Zeit based in Hamburg, Germany, and I will lead you through this talk and also moderate the Q&A session after the talk. We're going to have Slido questions. Unfortunately, you who are here cannot ask questions in real life, so you have to go through Slido, which is a bit weird, we know, but that's how it is. And I'm very happy to have as a keynote speaker and the person who introduces our speaker later, Michael Mann, who's the EU's special envoy for Arctic matters and who's going to join us from the not exactly Arctic city of Barcelona. Prior to that, he was the European Union's ambassador to Iceland. And before that, he has worked in communications and journalism. He was bitten by the Arctic bug when he was traveling to Kiruna and to Svalbard. And he told me how he has witnessed firsthand the dedications of scientists working there under quite extreme condition in a very remote environment. And ever since then, fell in love with this unique ecosystem. It's an honor to have you, and welcome, Michael Mann.
Thanks very much indeed, Fritz, and thanks also to the organisers of this event for asking me to say some opening words at this session devoted to MOSAiC, which is truly the expedition of the century. Over the 5 legs of the expedition, a total of 442 researchers, Polarstern crew members, young researchers, teachers, and members of the press took part. 7 ships, several aircraft, and more than 80 institutions from 20 countries were involved. And with researchers from 37 different countries, MOSAiC was an amazing example of international scientific cooperation at its best. Let me also acknowledge the massive role that the Alfred Wegener Institute plays in polar research, including its very important role in EU-funded projects. For example, the Institute coordinates EU PolarNet, our action which aims to establish a European polar research area, and many other significant projects besides. MOSAiC took the Institute's contribution to another level. It was truly an outstanding scientific endeavour. The goal of the MOSAiC expedition was to take the closest look ever at the Arctic as the epicentre of global warming, and to gain fundamental insights that are key to better understand global climate change. It's produced huge amounts of invaluable free data which will feed generations of scientists around the world and take climate research to a completely new level. This will contribute hugely to our understanding of the effects of climate change in the Arctic. It will form the basis for future research, which will help us to understand better the processes at play and design strategies and technologies to mitigate the effects of climate change, not only in Arctic regions, but throughout the world. Until now, the Central Arctic Ocean has remained something of a black hole in terms of understanding the processes at work in the ocean, in the ice, and in the atmosphere, which are of tremendous importance for the weather and the climate. Understanding these processes is important not just for the region itself, but for broad expanses of the Northern Hemisphere, and consequently for a large percentage of the human population. The discoveries made during the MOSAiC expedition have removed some of this uncertainty about future ice melting scenarios and will feed into vital research for years to come. The measurement data it's produced will be extremely valuable, not just for the participating researchers and their peers around the globe, but for humanity as a whole. From 2023, everyone in the world, from school children to NGOs, political parties, corporations, citizens, will enjoy unlimited access to the MOSAiC data. And of course, the EU will also be among the beneficiaries of this work. Among the scientists who took part were researchers from the EU-funded consortium, the European Fisheries Inventory in the Central Arctic Ocean. This international consortium mapped marine ecosystems in the area to support the implementation of the very, very important international agreement to prevent unregulated high seas fisheries in the Central Arctic Ocean. This agreement takes a precautionary approach to potential medium or long-term fishing opportunities in the area. No fisheries can take place until scientific evidence exists that it can be done sustainably. The data collected by MOSAiC will also be key for contributing to EU climate change mitigation and adaptation efforts. Indeed, the philosophy behind MOSAiC is very much in line with how we approach Arctic research in the European Union. Research and innovation play a major and key role in our new Arctic policy, which was published 3 weeks ago today. We see our Horizon Europe framework programme as the perfect instrument to foster international cooperation in Arctic science. Over the past 7 years, the EU has invested around 250 million euros in Arctic-related research under Horizon 2020. Many of the EU Arctic cluster projects concern predictions and modelling of climate change impacts in the Arctic and will be helped by the data collected by MOSAiC. And we will continue our considerable support to Arctic science via the Horizon Europe programme, which lasts from this year until 2027. That work will be all the richer for the huge contribution of MOSAiC. Again, thank you very much for asking me to introduce this fascinating session. And now back to you, Fritz.
Thank you, Michael. And before we let you go, can you tell us about the moment you fell in love with the Arctic when you were in Svalbard and in Kiruna?
Well, I was very lucky enough to go on a trip with my then boss, Catherine Ashton, the High Representative Vice President of the Commission. She'd been invited to first to Rovaniemi in Finland, and then Kiruna in Sweden, and then Svalbard in Norway by the respective foreign ministers of those countries. And it was just a fantastic trip. Obviously, there was lots of work and meetings involved, but we saw incredible things. We went down the iron mine in Kiruna. We went right up to Svalbard. And in Svalbard, what really got me was the fact that there were a great number of scientists, researchers who were living rather almost lonely lives, actually, but they were so dedicated to what they were doing. It was fascinating to watch them. And it's just when you go to the Arctic regions for the first time, you just see this magnificent scenery, and it just blows your mind, basically. So I was pretty much smitten then, and lucky enough after that, of course, to go to Iceland for a couple of years, and now to have this fantastic job. So I'm a very lucky man. But we have work to do, because obviously the Arctic is melting, heating up much faster than the rest of the world. So it's pretty much a crisis situation. So we're trying our very best to do all we can with our international partners to try and mitigate that a little bit.
Yeah. Well, thank you so much, Michael. And the organizers have set the right scenery, because the room is so hot. It's so we definitely feel that this region is doubling or is gaining heat more than any other region of the world. And very interesting what Michael, thank you to Barcelona, and what Michael said is also can be applied to you, because you also started very early with this passion for the Arctic. You are a sea ice physicist at the Alfred Wegener Institute for Polar and Marine Research. And more importantly, the reason why you are here with us today is because you are one of the masterminds and architects of the whole MOSAiC expedition, and you've been working on this since 2008 already. And you're going to share some of the key findings of the expedition. And you said before that you can compare an endeavor like the MOSAiC expedition with the challenge of fighting against climate change. In order to succeed, we have to get things going and be optimistic. So yeah, very much looking forward to your talk, Marcel Nicolaus.
Thank you. Kein Trailer? Okay, yeah, welcome everybody. Thank you very much for having me here today. I'm very pleased that I can talk about MOSAiC, the greatest Arctic expedition of our time. For me, it's a really honor to be here, because I think this also shows that with MOSAiC we did not only bring successfully a field campaign of a big project to an end, but also we really made it into society, into political discussions. We brought the Arctic, the climate change, one step closer to all of us. And to me, as already introduced, MOSAiC is also a great example how a very diverse group in the end succeeded with one common goal. Although there were various challenges across the way, I will show you that in a minute, but really we reached that built on our optimism and the will to have a complete and successful expedition. I would like to start my presentation with my personal favorite photo, a photo from the Arctic night. Because this landscape really illustrates the very magnificent Arctic landscape. I took that photo a couple of kilometers away from Polarstern in a silent, dark region. Now you might wonder and say that's not dark here. But the only light spot here, that's the moonlight. That was the only light we had during the polar night, and that moonlight created this mystic landscape of a landscape that's really changing rapidly these days. The Arctic is the epicenter of global warming. We heard that already. So that figure here introduces us the temperatures of last year compared to period 60, 70 years ago. And we can see that global warming is ongoing everywhere, and in particular, if we look into the Arctic, we see that the Arctic air surface temperature has increased by more than double of the rest of the world, far beyond the 2 degrees, beyond the 4 degrees, and it has exceeded these 2 degrees everywhere quite a bit. So these warming rates are really extreme. Bling. Okay, so the change in the Arctic is dramatic. That's what I just showed. But still, for many of us here in the room, I think that change is just happening in the newspapers. And you probably think the Arctic is far away. But I can tell you the Arctic is much closer. It has much more effect than many of us can imagine. From here to the Arctic, it's closer than from here to the Mediterranean. And when I remember back to 2002, that was my first own field research in Svalbard on a fjord. We went with ski-doos and skis to sample sea ice. And since then, in the last years, the fjord has not refrozen. So nowadays, you would need to take a boat trip there, and you could not do sea ice research as such. So it is closer, and it is changing rapidly. So what's the future of the... I'm a bit struggling with that thing. Okay. What's the future of the Arctic sea ice? I mean, everybody in this room certainly knows the Arctic sea ice is changing, it's declining, and that happens rapidly. So we see the time series from the 1970s, when we started with satellite observations of the extent, so that's the area covered by sea ice, until in the end it will reach to today. If we look to 1997, when the Kyoto Protocol was established, we had a slight trend. At that time, we could say the sea ice is an early warning system, something is happening. When we move on to Montreal, when things get more into action, and even until the Paris Agreement in 2015, now we see there's a dramatic decrease. And that dramatic decrease, with something like 13% per decade of ice loss, continues. And it will further continue. So the IPCC report says the Arctic is likely to be practically ice-free in September, at least once before 2050. So that's 30 years from now. And beyond that, we will have more and more open water in the Arctic. Because it's not only the extent that's changing, the ice is thinning, it melts earlier, it freezes later, the open water season is increasing. And this has consequences for us here in the lower latitudes, for sure. That image shows on the left-hand side the classical situation. We have a cold Arctic, the warm mid-latitudes, with a strong temperature gradient that drives the jet stream circulating around the Arctic, and keeping the cold air there and the warmer south. With that engine becoming interrupted more and more because of the decreasing temperature gradient, it starts meandering. And that has consequences here on us in Europe and Northern America, for example. It allows more and more cold air outbreaks to the south. It attracts more and more heat and moisture into the Arctic. And with that, we get more into extremes as we start to observe them in our news everywhere in different places over the world. If you look further into the future, what's happening next? Here again, I come back to the IPCC report. We see projections of the temperature towards the end of the century. And we look from the left in the figure, from the Antarctic over the equator to the right to the Arctic, and we find that warming is above 2 degrees Celsius in all the regions based on the scenario. And the width of the dark blue stripe, these are different models. But then we also see the Arctic is increasing by 5 to 15 degrees. And we see that with that increase, the variability is much, much higher. So we can really see that many processes in the Arctic system are only barely represented and understood in our climate models. So it's a huge uncertainty. And to understand this is key, and we have to work on that. And for that, we have to base it on more and new observations. And then MOSAiC comes into play. The challenge is really to understand our future better, but what to study exactly. We can see the different spheres, the atmosphere, the ice, the ocean. We have the physical, the ecological, and the biogeochemical environment. And most research in the past was driven within these disciplines or categories. But now we have to describe all these arrows, all these linkages you can see in that figure. So we really need to understand the coupled system as a whole. And only with that we will be able to improve the forecast as we had on the last slides and reduce all these uncertainties. So we set out with 5 teams and one common mission to understand what are the causes and the consequences of the Arctic sea ice retreat. To study it from these 5 categories that I had before, grouped around models that need to be improved for better understanding in future. And within that, we have a lot of specific challenges. The energy exchange between the atmosphere, the ice, and the ocean. How is that varying in different seasons, for example? The formation properties, the life cycle of clouds and aerosols obviously play a big role in that. The exchange rate of gases or climate gases in particular and the transport pathways in the Arctic. What is the reaction of the ecosystem? I mean, there is a change ongoing, but how does it react and what timescales does it react? And what are the global consequences? And in addition, there's also the common goal to really get to the point to bring this knowledge into society, to feed the results into our climate discussions. So, if we want to understand the Arctic, we need field observations in all seasons, in all disciplines, at all scales. And if you have the right side of that illustration here, you can imagine that's the real nature. But we have to transform that into models. That means we have to find a lot of small wheels and connections and chains, like in an old watch. You can see. So we have to describe all these elements in there and how they reach into each other to make, in the end, if you compare to the watch, to show the right time. And these needs, in our terms, that means we have to describe the processes, we have to couple these components, we have to really enable more reliable predictions. And that certainly needs an expert consortium. So we need to bring the best methods, the best tools, the best experts together. And it's a bit like here in Glasgow. We have to bring all the different components together to discuss it together to get to that common goal. So, the MOSAiC expedition. How can we reach now the Arctic in winter? It's obviously not as easy as that you can just go there by a ship. And then comes the first idea. Oops, we lost that. When Fridtjof Nansen did an expedition in 1983 to 1986. He was a real pioneer. He set out his wooden vessel Fram based on the idea there must be some indications here, there must be this transpolar drift. And as a pioneer, he was really that optimistic and looking to the future that he said, okay, he was able to raise the funds, to find a crew, to go out to an expedition. He had no idea where that would end, but he made it over the time across the Arctic Ocean. So by going in, freezing and drifting with the ice. Okay, we chose the same process in the legacy of Fridtjof Nansen. We used now a fully equipped modern research icebreaker, and we performed a well-coordinated and consistent program that we called MOSAiC. And just to spell it out once for you, it's the multidisciplinary drift observatory for the study of the Arctic climate. And that should result in the largest expedition ever, having 7 icebreakers or research vessels from 90 institutions. We heard some key facts already earlier, and 450 people with that one mission. And that mission is commented by a few colleagues now in the video that we would like to show you. The one mission, the one world introduction to MOSAiC by several colleagues.
Sadly, in my lifetime, I think we will see what it really means to have significant ice loss in the Arctic and what those implications are.
В 2006 году в Арктический институт приехал профессор Клаус Детлов, который предложил координировать работы в Арктике на дрейфующих станциях с институтом Альфреда Вегенера.
19 nations coming together, that's really remarkable. We really are organized under a shared vision.
Given that we were strangers, most of us were strangers to begin with, and at some point, we just found a way to trust one another and to rely upon one another, and most importantly, to support one another.
MOSAiC ist ja damit wirklich weltweit eine große Ausnahme. So gelingt es uns durch den gewaltigen gemeinsamen Einsatz aller Beteiligten hier und diese Expedition auch unter den ganz schwierigen Bedingungen der Corona-Pandemie fortzuführen.
I feel that the future of Arctic science is really going to be in good hands. We've got this whole new crop of young people that are coming up, and MOSAiC is helping to lift them up into this kind of new world of Arctic research as we unravel the puzzles of the changing Arctic system.
Okay, so Matt Shoup, one of our coordinators, said to unravel the Arctic system, and I mean that's what was our mission, what we are still working on. So to get back to slide 14. One back. Okay, 1 year in the Arctic Ocean. If you look to the right side, so that was the track that we took with Polarstern. We left in Tromsø, went along the Russian coast to the north, froze in the beginning of October, and then drifted really quickly south and much faster than what we expected. We'll see that later. So due to that, we melted out of the ice flow disappeared in summer, so we had to set back in order to complete the annual cycle with a second drift close to the North Pole in autumn. And during that time, we experienced, and now I call it the ice clock on the left-hand side. We started in September, October, just before it got dark, with thin and new ice. We went through the very rough winter, the cold season when most ice was forming, into spring, when the sunlight came back and really changed processes again, into the summer when the ice started melting from the surface, breaking up, and then even into refreezing again. And this cycle in the Arctic goes round and round, and we were able to witness and measure that cycle once. I would now like to take you through a collection of photos along that year. And starting on 3rd of October, with the last exchange with the Russian icebreaker academic Fedorov. That icebreaker helped us to set up the distributed network, a lot of distributed stations around, helped us to find the flow. On board there was a MOSAiC school, so this is the next generation of climate and polar scientists that really were involved in MOSAiC. The next day we arrived on the 4th of October on our ice floe and started the drift. And we really arrived there on the last possible day, you could say, because then it would start getting dark, and the darker it gets, the harder it is to establish an ice camp on an unknown ice floe. So we were really there in time, and I would like to say, as we are here in Glasgow, we are really here just in time. Going into the darkness in October, the ice was very dynamic. I remember we kind of every day fought with the ice when the ice started to pull on the cables, varying instruments, pushing, moving instruments around. I remember one evening standing on the bridge of Polarstern. You can imagine the ice camp around us. And then the Met City, I will tell you later, the meteorological station, just moved several hundreds of meters across in front of us. I mean, oh shit, where is that going to stop? Luckily, it stopped, but still it meant for us to rebuild everything once more. We had sites like the dark side, the red light district here. And that was so red light because we didn't want to interfere with the ecosystem. So bringing bright lights there in the darkness would have disturbed the environment. So this and other measures had to be taken in order not to interrupt and interfere with the environment that we want to measure. So all work there happened in red light. And in addition, taking one ice core, we can measure so many parameters on it. We spent so many workshops beforehand to coordinate how to cut the ice, how many cores we need in order to optimize it, because you can't take 100 cores on one day. Maybe some days we even could, but in general, there was a lot of preparation ongoing before. I also like that photo because that's a combination of high-tech technology that had to be adjusted for the use in the field with heating and coverage. You can see the different light spots that only allow to work. And here we measure surface topography, meaning the roughness of the snow and the accumulation of snow. And if you do that again and again, you can see how the snow on the ice moves around over time. A remarkable event end of February, when the Russian icebreaker had to fight all the way until 88.5 degrees north. Never a conventional ship has been that far north in the winter in order to resupply us. And for me, that's symbolic in two things. The one is the will and the need to succeed this expedition, because that was the only way to get there. And the second is the change of the ice, because that would never have been possible 20 years ago to get there and to have any resupply for us out in the darkness in the ice. Now light comes back. We have balloon towns where it's a tethered balloon that we can launch and recover on a regular basis from these tents in the Arctic to measure the atmosphere conditions. Or when the sunrise came back in March to see the ice camp. So you can see some of the installations around. So the ice camp spread some 1 to 2 kilometers around the vessel. As I mentioned, there were other stations further remote of that. But you can really see Polarstern as the heart of it, equipped from the bow with measurement masts. On the roof there were antennas, on the aft deck there were containers, so it was completely stuffed with scientific high-tech and all our laboratories. And it needed passion. I mean, sitting in the snow pit kind of every day, you can see the slightly blowing snow here, sampling snow, that's the work you get cold fingers and cold toes. I mean, you have small plastic bags with vials, you want to put some snow in, and you take one snow pit and you get samples from many institutions around the world to measure all the different parameters on it. The other scale is to have a sonde hanging on a helicopter. Here the EM, the electromagnetic bird, we use to measure ice thickness about over tens or hundreds of kilometers around the ship to map the area in a larger scale, because that's also needed for our understanding, not only the small scale, but also the larger scale. And then the pandemic changed everything. So our original exchange plans didn't work any longer. We couldn't get an icebreaker that supplies Polarstern again in the ice. So Polarstern had to come out to Svalbard, met there 2 other German research vessels to meet in a fjord to get resupply, to get an exchange of crew and scientists. We should never forget the crew in here, because they also did a tremendous job to support us, to supply us all year round, and they also needed that exchange. And on that day, I remember that on my first day on Polarstern, our captain Schwarze said that now with Polarstern we go on a real expedition, different from a classical fieldwork or a scientific cruise, because we're never going to know what's happening. And on that day, that was one of these days where we didn't know if that would succeed, if that would continue at all, but we made it. We did that exchange, and then we're able to go further north again. And find another flow with now strong melting conditions. And I like this photo because you have really this kind of round-shaped pattern of the flow with all the melt ponds. I really love them. It's great to see. It's unfortunately it's a matter of melt, but it's really great to see all these melt puddles on the ice. But just a month later, 31st of July, our flow decayed due to wave interaction, due to dynamics, also due to melt. The ice was very rotten. Luckily, we started to recover our camp beforehand, so we didn't lose anything in the ocean. But with that, MOSAiC Flow 1 was gone. And what was the option then? We had to set back. We had to go north again. In the year of 2020, the ice north of Greenland was very rotten, very open, so we could rather easily go to the North Pole. Also found there a very melted landscape, but found another flow, our home for the last month of MOSAiC, where we then studied the new ice, the thin ice. You can see we set up a new camp close to Polarstern with many installations in order to complete that annual cycle, now describing that new typical ice of the Arctic. Have a look from the top, also gives you an idea of the dynamics again. When we came, it was one flow. Now you can see on the right-hand side there's a little break. On the left-hand side bottom, this piece was once connected to the other piece on top. So it's dynamic, but we were able to work on it. To the last day on the ice, 20th of September. So when the sun set, sunrise again is kind of one thing. You can see me sitting on the very left here on the photo, enjoying the last sunrise or sunset on that day. Before we had to go back to Bremerhaven, where again a remarkable event was that we had a really big reception. Although there was a pandemic around, we had many ships that guided us into the harbor, sailing boats, big boats, tourist ships, colleagues, friends waving at the pier. It was one of the moments, probably like also when Nansen and other expeditioners came back and everybody celebrates that they made it well back home. Those are impressions, and I mentioned the logistics, and I want to have 2 more slides on logistics here today for the Arctic Ocean because it was a logistical event. The pink line on the left-hand map, that's the Polarstern route that I introduced earlier. But now I want to focus on all the many other lines, because this is what was necessary to make that one pink line happen, with all these different icebreakers you see on the right-hand side, selected and chopped into 5 legs over the year, and to enable all that exchange, even to aircraft we had for an exchange in April. So it was certainly a unique logistical challenge for us, for our logistical team, for the Russian colleagues, and for all the others that were involved, because otherwise we couldn't have done any of the science with that background. And on the ice, we had our own city, ice camp, logistics. To start with Polarstern, I mean, Polarstern was not only our home, it was our helicopter base, it had all the labs, it had all the resupply for us. It was a basis with many instruments. And out on the ice, we had the Met City, so the meteorological station characterized by a 30-meter tall mast measuring atmospheric conditions. We had the balloon town that we saw earlier, where you could launch the balloon, get it up and down, also for atmospheric measurements. We had the remote sensing site, so in space, many satellites followed us. But here we set up the same kind of antennas and instrument on the ice, and there we were able to measure right in front of them what they really measure. So how do these signals match to what happens on the ground? We had the airborne measurements connected to Polarstern, obviously. And if you look one level down, we had the ocean city, measuring everything that happens in the ocean, connected to the winches on Polarstern. We could even look down all the way to the sea floor. So now we span from kilometers to top to kilometers in the bottom. And the ROV city, the ROV, the remotely operated vehicle that was able to dive under the ice. I will show you some under ice impressions in a minute too. So this was our camp, and all connected through wires of electrical cable, of roads that we could walk and drive on data lines, so everything a modern research infrastructure needs. And this camp, basically, if you could look into a schematic, that was our central node within 5 kilometers. So there where we could mostly study the processes. If we look one level up, our distributed network within 50 kilometers, we had unmanned stations, we had some helicopter measurements out there. That would then, if you transfer to a model, be the grid cell of a climate model, for example. And we had observations on the next bigger scale, the entire Arctic. If we look into our satellites, if we look into other vessels that took measurements and other buoys that took measurements, and now we talk about regional and climate modeling. And now our challenge is to get that all together into numbers to improve these forecasts, as I said. I want to take you through a few more impressions. What drove us during MOSAiC? The isolation. So it was not only dark and cold, we were really remote away. The next human being some 1,000 kilometers away down in the Arctic. The darkness. I gave you impressions already, but here again, I mean, if you do a snow pit, I mean, you can really just see what you had to see. If you walk around, you're very limited, but it was possible. A few numbers on the ice camp. So top left is Met City, the ROV city on the left-hand side, the remote sensing, but it was more than 100 tons of equipment, 5 kilometers of power lines on the ice. So we had to measure more than 100 climate variables at a time. Yeah, and we tried to maintain them. So a lot of the work that we did in the field was not only measuring, but just maintaining these instruments that were out there to keep functioning. It was obviously cold. I brought some frozen faces here. We had really temperatures like minus 40 degrees with wind chills even colder. And here that's also a difference to maybe the early heroes of polar research. It was our first aim to get everybody safe and well home. So we didn't need the heroes out here, but I mean, the days were cold and long out there. And obviously connected to the cold, we had storms storms that buried our equipment, and usually we had only a rather short time to react, because after the storm, when the cold comes back, everything freezes together. So you have to get your gear, your equipment out of the ice bunches before they start refreezing everything together. And the storm leaves pressure ridges on the one hand side that were a fascinating object to study, also a logistical hazard, but how these pressure ridges form and how they evolve over time is one of our research questions. And while the ice piles up on one side, the cracks open on the other side. And those are the factories of sea ice. Whenever the ice goes open, the ocean freezes much faster. Thin ice grows faster than thick ice. And that's another of the fascinating stories to tell. And the new ice is the new Arctic is characterized by much more thin ice than the old one. Obviously, polar bears, quite cute to look at when you're on a safe ship. Makes you a bit more nervous when you're out in the field and you can only see that far, and you know there are some polar bears around you. So we obviously had to have permanent polar bear protection all around us. And in summer, I said I find them still fascinating. It was a big topic from all disciplines in summer. Melt ponds, what is their role? How do they change energy exchange? How do they change gas fluxes, for example? But still, if you just look at the images, it's just pretty, and depending on the light conditions, very different looking great scenarios and features. So I said I brought you some impression from under the ice. Now I would like to see some movie shots from our ROV under the ice, introducing that work. Okay, so. To get the RV out of the water, but those were some impressions from under the sea ice. But beyond these visual impressions, we also brought obviously results, numbers and facts. And now I thought to come back to some numbers and impressions from the Arctic. Here we go. So I brought again this image on the left-hand side to transform from observations to models. And what we really see is that winter temperatures have almost been 10 degrees higher than what Fridtjof Nansen experienced 130 years ago, and the ice was half as thick. That was a winter observation. And in summer, we've really seen and experienced the melting of the ice, the decay of the ice, and how the new Arctic, the dynamic Arctic is in summer. And to put it into numbers, we brought a data set for generations, and I'm sure I'm not exaggerating. We just started to look into it. Most samples are still liquid water, snow, or whatever, ice cores. So we brought 150 terabytes of data, 10,000 of samples, and they will, over time, allow us to represent these processes better in models. We have already more than 30 peer-reviewed scientific publications, something like a week coming, a new one in addition right now, and obviously high-impact media news, and I'm really happy that we can be here in that session and also to share that in an event like this one here. Today, the new scientific insights that we can already say now, as I said, most will be to come, but the fast ice and the high drift dynamics that we experience. The picture to the left-hand side from a publication by Thomas Krumpen and others shows the anomaly of ice drift. So the more red, the faster the ice is, compared to a period 10 years ago. And there we can really see this transpolar drift stream, the red line that took us along and that showed why we were so fast along that track, while the ice was so dynamic. The new scientific insights under the ice and in winter, there are many firsts of that. And I brought one example from Christian Cutler in our publication here, where we found a typical or atypical for the Arctic, but something that we observed in the Antarctic so far only, platelet ice formation on the under the sea ice. So a formation process of ice that is different, that was a hidden process, but these processes that we can reveal now based on the winter data that we didn't have before. The ocean, this is the time series of the ocean temperature that we measured. And we see from that work of Benjamin Rabe and Jakob Bölter that we have an increased heat input. So we have more heat coming from the ocean to the ice than what we expected and than what it was before. And if we look, for example, into the snow and all the changes, I brought a schematic in that case, because we need to be, and now we will be, able to have new descriptions of snow on sea ice. Snow is so critical in many phases for the energy budget, for the insulation, for gas processes, for the ecosystem. And it's so dynamic, just blown around by the wind. So there are many arrows in that left-hand figure that we can now put numbers on, or we can put numbers on in the next years. And pathways of trace gases like CO2 or methane, I mean, obviously climate drivers here, as we know, through the Arctic. I don't have a figure here yet because those samples are for most still in numbers, but we know that we have these data, these samples along the pathways of the Arctic sea ice, and we can follow them. So there's a lot of great science coming week by week now. And even next, we have also an EU-funded big project, because one of the things that we can still do better even after MOSAiC is to involve indigenous people and community in it. So, and this is a project that really has the goal to achieve Arctic observations together with people living there, to combine our monitoring efforts with their knowledge and efforts. And we are really glad that this project got funded and we can work along these lines in the next years. And with that, I would like to thank all of the MOSAiC people, participants, crew members, people on land, in the background, in the logistics, wherever. I mean, these 5 photographs show the 5 teams that were in the field, but there's at least as many people that were not in the field, that were not on the photos, but that made it all happen. And there's even more people in the next years to come, including all our new students, to work on all the data that we brought home. And yeah, here I would like to thank the organizers of that entire pavilion here for to give us the opportunity here today to talk, to share these impressions. And I really wish you inspiring discussions here around it. And for me personally, I think we can take a lot of things home from what we learned during MOSAiC, not only on the science, but the way how a very diverse group had a big vision, how they realized it, whatever came along. So be optimistic about the process, and thank you.
Thank you, Marcel. As someone who lives far away from the sea, it's like the first time that I understood how you can build a career on researching ice, because I know ice as an ice cube from my freezer, but it's actually like what we've seen in your talk is that it kind of lives and it's dynamic and that it's active, you know? It's not just like a frozen piece of water.
No, I mean, it's very, very active, very dynamic, and it's really fascinating. And we are far away from that ice sheet is one level, you have a little snow and ice, so it's so dynamic, it's so uneven. For me, it's just a big fascination how also wind and ocean are able to move these masses around, and how a little sunlight in summer can change everything within hours.
We have a question from the audience. Does the movement of the ice mean that it's melting faster and that it's less stable?
There's a link between the thickness of the ice and the movement, yes. I mean, it's a bit what comes first, but yeah, so we see the ice is thinner, with that it's more fragile, and if it's more fragile, it's easier to move because of internal friction is less or different.
Another question from the audience, and I would also suggest, because it's quite complicated with Slido, if you have a question from the audience, you can ask it and I will repeat it so our people in the audience and live stream will also hear it. So we're just going to do a question here. Over the past couple of summers, there have been reports of unusually warm summers in the Arctic. What has been your experience compared to Europe? And I think this question asked about the link of the weather patterns in the Arctic and the weather in Europe.
Yeah, I mean, on the one hand side, we have to be careful. We cannot link a day or a month of warm temperatures in the Arctic with a specific event in Europe. That doesn't work. But overall, we can see the tendency that the warmer Arctic and the reduction of the temperature gradient that I introduced earlier, that this has a strong effect of how the big atmospheric circulation patterns work and how this might lead to blocking situations that cause these extreme events, how that has exchange with air temperature and humidity between the Arctic and here. So yeah, more of these extreme summers will give more extremes here, but you can't make that one-to-one day connection.
Was there a question from the,
Yeah, I have a question.
So we have a mic actually. Okay, lovely. Thank you.
Thanks. Is it on?
Should be on.
Yeah. It's okay?
Yeah.
You had professional media people on board as well. I mean, the pictures or the videos that you showed here were clearly made professionally, and I know that you also made or there was also a TV documentary made for it. So I'd like to hear more about the media part of the expedition.
You want to repeat that?
Yeah, I think we have it in the live stream because we have to.
Yeah, so I mean, there was obviously a large media interest from the very beginning on, and yes, we had media people on board on every leg, and these were mostly organized in a way that they produced material that then could be used by other media at home in a kind of a pool, because we couldn't take as many people on board as they would have wished. But yes, I think that's an important part, that our communication about our work has changed and is still changing, and this is much more active. And yeah, that was great to see.
Before we go to the question from the audience, I have a question here. There was a question about the data release. So can you explain a little bit, because in the question it indicates that all the data will be free after 2 years. Is that correct?
Yes. So the data policy says that we will release all data by early 2023.
The raw data, actually.
The raw data. Obviously, we have a large consortium of scientists already now in the world. They are actively working with this data. We are still endorsing more projects that can come to us, contribute, and work with our data. So we try to be as open, and even before the 23, right now, most of the atmospheric, most of our buoy data, part of the RV data, etc., they are already available. And if people are interested to work with that, get in touch with us. We'll find ways even before that.
Even the cute polar bear pictures?
Even some cute polar bear pictures, but I have to admit that with media, that's a bit more difficult than with
we don't want to go there, okay. Okay.
So I was just going to ask, at the start you had the sort of different layers of what you were measuring, so in terms of the atmosphere and then the ocean and the ecosystems. I'm wondering how you measured the ecosystem part of it. So were you tracking fauna? Were you, there was measurements, I guess, plankton or that kind of thing in the ocean. Could you talk a little bit about that?
Yeah, so the ecosystem part was certainly a big one, but we did not tag or track individuals. So it was more about understanding the ecosystem. So a lot of primary productivity on algae, on fish, on different stages of the fauna, and how they interact, what they feed on, how they survive, what they have for strategies. So it's more on this, I would call it as non-biologist, on these microorganisms, not, we didn't tag polar bears or seals or something, because also their lives is on a different scale than what we can really observe in that ice camp. In that ice camp, we can track if algae prefer to grow under thicker, thinner ice, ridged ice, level ice, melting ice. But it doesn't work for the big ones.
There was also a question from the on Slido about insights on the ecosystem. Do you want to add anything from there?
I can certainly add to that most findings of the winter are new, because simply there wasn't work like that. All these strategies that the ecosystem has to survive the darkness I think there will be exciting results, types of fish that were caught that we might not expect, etc. I mean, I'm not into detail with the results, but yeah, this kind of work, I think that's really groundbreaking here.
And that's already partly being published, but
that's partly being published. But the ecosystem, the biogeochemistry, these disciplines have the most challenge that it's a long way from a sample to a data point. And yeah, we mentioned there are now 40,000 samples. Most of that is still either frozen or liquid water, or maybe filtered on filters and deep frozen. Yeah, so that route is going to be a bit longer. While in the physics, we often have the advantage that temperature data, I mean, they just come in, and there they are. They might need a little calibration, but you can work with it. But the other things are mostly samples in the first place, and then have to go a long way.
Okay, we have a question there.
Thank you very much for your presentation. According to your experiments and everything you have experienced in the north, I was wondering if you could see any similarities with the Arctic and the Antarctic. Of course, the geography is totally different. The Antarctic is a frozen continent surrounded by ocean. The Arctic is a frozen ocean surrounded by Earth. So is there similarities? Is there some features that we can observe in the Arctic that are similar in the Antarctic, or is it totally different?
Yeah, I mean, that's indeed a great question, and that really comes to the Antarctic paradoxon. Why is the Antarctic ice changing differently to the Arctic sea ice? Because obviously the physics is the same on both spheres, but as you already said, the geographic setting is very different. You have the cold Antarctic inland ice sheet that has continuous downward flow of cold air that impacts a lot of the sea ice differently to the Arctic that's surrounded by continents. So some processes are the same, or the physics is the same, but they are controlled by different mechanisms. As I said, so for example, some ice formation processes, we know them from the Antarctic, and we'll see how that might now also come to the Arctic. And some melt processes we don't see in the Antarctic yet, but with an ongoing change there, they might come up. So yeah, exactly as I said, I mean, we can talk about that for a while afterwards. But yeah, that's a fascinating topic. But that brings me also to one of the questions, what comes next? I think doing something like that for the Antarctic would be enormously valuable and would then bring the comparison. But that's even more challenging with the logistics.
We have some questions from on Slido, which we can probably go through very quickly. What was the typical thickness of the ice flow used for the drift by Polarstern?
When we came, we were around 1 meter, but we chose a core of the flow that was beyond 3 meters as a stable core. Yeah, but it went from 1 meter to 2 meters or something, and then into melt afterwards again.
And I think, in my understanding, also the older the ice is, the thicker it is. Is that correct?
Mostly, yes. The rest is details, yeah.
We're gonna discuss later. Another question on the science is on how much of the analysis could you do on the site while being locked in or frozen, and how much follows later on stored samples?
We really focused on collecting data in the field. We did almost no analysis. We did some, obviously, I mean, to pick sites, where do we do what? So we did some, but those were only made to guide decisions on board. The real analysis all happens at home. There
is a question on the polar vortex. You showed us the demonstration of this year's polar vortex. How does the data prove to increase likelihood of this event?
Sorry, I don't get that.
Is it likely to increase that the vortex is being
so the
broken?
The vortex is basically a result of the temperature gradient. And the more the temperature gradient reduces because the Arctic is getting warmer, the more the vortex is going to meander.
And that's robust science already.
Yes.
There is a question from also a rather personal. I don't know if you want to answer how you personally. You said before that in these days it's hard to find someone going on an expedition for a year like Nansen did. You went on different legs, each lasted 3 months. How did you prepare for that?
Oh, I mean, for me that was really a huge motivation. I mean, I've worked so long on that project. For me, when the question came out, it was clear if I could go, I would go for sure. How do you prepare? I mean, for that time you have to do obviously a lot of compromises at home and around. But
do you have family?
Yeah, yes, also that. But you have to. Yeah, I mean, it's part of the job and it's very exciting. and you get a big reward when you come back with all that afterwards.
I mean, it was very clear when you gave your presentation how passionate you are about, and you also used words like passion and stuff like that. Do you find that you have the opportunity to put these emotions into presentations, or when you talk about data, is that something that you allow yourself to?
I mean, yes, and I think it's important. I mean, if I would stand here and just read you some numbers, probably nobody would want to listen to that more. I think emotion is important, and also if we talk about that climate process here, if people are not optimistic, emotional, and really put a lot of personal effort into it, it's not going to work. So we need that passion and emotion, and we can't do an expedition like that with work from 9 to 5.
You also talked about, you stressed that several times, that it's important to train a new generation of scientists. You talked about the MOSAiC school on board of the Russian icebreaker.
Yes.
Do we even need sea ice researchers in 50 years? I mean, it's all gone by then, no?
I mean, we talk about the summer sea ice is gone. I mean, the winter sea ice will for sure last much, much longer. And it's not only the sea ice. I mean, these researchers, they don't only work on sea ice. The connection is to understand the climate system, and the climate system will be there with more sea ice in some phases, with less sea ice in other phases. But I think to really understand these things, from atmosphere, ice to the ocean, from the ecosystem to the physics, that's really important. And yes, we need them, and we need them even more interdisciplinary as we needed them before.
We have a question here. I don't know where the mic is. Yeah, there.
It's a bit of follow-up on your questions. What do you say? I mean, you presented lots of challenges. What was the one moment that was sort of the most difficult or challenging in the entire year? And also, what is the thing that went surprisingly well?
So the most challenging part, I think, is in many cases the mental state. I mean, to go out there and to do it again and again and again. Because you know, especially when we were on the first leg, you know, you set it up for an entire year and you have to do it good. So that was certainly stressful, and yeah. And on the third part, it was certainly the corona pandemic at home for people, because they're very far away. They had rather little clue of what's going on here. The world changed and they weren't there. I think that was the main stress for many of them. What went well was really the teamwork. I mean, the spirit that we had in the team from the preparation. You have to understand it's a very international, very diverse group with very different expectations to these things. And to bring that all together into one experiment, into a consistent time series, that really worked as well as we hoped for.
We have a question here, and we have about 3 minutes left. Just for here, and the lady with the, yeah. Thank you.
Thank you very much. I was really impressed, as you just said, about what you managed to organize. Because I imagine when you are there, you need to have everything already prepared and set up in your mind in a plan. And can you tell us about more about how you decided what to measure, how to measure it, and you probably already had an idea of what you wanted to achieve at the end. Of course, not about the results maybe, but what you wanted to achieve at the end with the results outcomes. And then after the expedition, how you extrapolated them, for example, from your on-site measurements, to show this extrapolation of the hot stream ice, for example. Thank you.
Okay, so that was quite a few aspects.
2 minutes, you can do it.
I lost it. I wanted to start with something in the beginning. What was the first point with?
About the preparation of
what to measure, exactly. So that was a long process. I mean, we prepared that for years. There was a negotiation between scientists. What is more important? And in the field, it was often that you had to step a bit back from your own work. I could have dove in the ROV every day if I wanted, but it was not in order to achieve the general thing. My help was needed in other projects. So I think there were these compromises. What are the key time series? And we defined a couple of them, and really to maintain them as good as possible, and then do little experiments in addition wherever possible. I think that was the main strategy. And the other part?
About the extrapolation of your...
The extrapolation,
Very quickly, please.
The extrapolation is mostly what we now do with satellite data and later with models. I mean, we had the point measurements here and the distributed network around. That was little extrapolation, but the rest needs more math and science afterwards.
All right, that was like 20 dense minutes of questions. So thank you to everyone watching us live, and everyone in the audience. And yeah, great job, and thank you for sharing, Marcel.
Yeah, thank you for being here.